Okay, so definitely some right triangle trigonometry will be on the final. Here you can see we're given a triangle and we're asked to find the length of one of the sides. We're also given the hypotenuse and we're given one of the acute angles. From this acute angle, right, we can see that we have the opposite side. Um, we can also see that we have no information, or we're not trying to find the adjacent side. I'm just labeling that. And this, of course, is the hypotenuse. And the three trig ratios that we've used, we know that the sine of one of the acute angles, theta, is equal to the opposite side or opposite leg divided by the hypotenuse. The cosine of one of the acute angles is equal to the adjacent leg divided by the hypotenuse. And finally, the tangent ratio, I'll put it here, the tangent of one of the acute angles is equal to the opposite leg divided by the length of the adjacent leg. So as I'm looking at this, I can see I'm clearly dealing with the opposite side. I'm trying to find that, and I know the length of the hypotenuse. So opposite and hypotenuse, I'm going to be using the sine ratio. So I would write that the sine of this acute angle, this 28-degree angle, is equal to x divided by 29. And to solve this, I would multiply both sides by 29. And I can see over here, this is a 1, right? 29 divided by 29 equals 1. So I'm left with x is 9 times the sine of 28. One of the things I always suggest doing is just verifying that you are in degree mode. So just hit mode and go down, make sure your calculator says you're in degree mode. But then just go ahead and multiply the 29 times the sine of 28 degrees and press enter. So for this one, I'm getting x is a rather long decimal. It's about 13.6146. They said they don't actually say to round it to a certain number of decimals, so probably 13.6 or 14ish is adequate. And you know, it's I like to verify my answer. I might take this number. I mean, this is the answer. But what I'm saying here is that 13.6146 divided by 29 should be the same decimal value that I see on my calculator when I look at the sine of 28. So if I divide that by 29, I get approximately 0.4694. And if I look at the sine of 28, I also get 0.4694. So this is most definitely the answer, about 13.6. On the next one, you can see I have the adjacent leg, so ADJ, and I'm asked to find the hypotenuse. And this is the angle I'm speaking of. And I guess it's important to recognize that, yeah, from this angle, this is the adjacent leg. So it would change if I was talking about this angle. If I was up at this angle, this would be the adjacent leg. But I'm not at that angle. I'm at the one that's labeled 65. As far as which ratio I use, the cosine ratio is the adjacent leg divided by the hypotenuse. So I'm going to go ahead and write the cosine of a 65-degree angle is equal to 101 divided by x. Now I'm trying to solve for x, and whenever my variable is in the denominator, I find it worth it to take the extra step and multiply both sides by that x first. Over on the right hand side now, I just have the number 101. So literally now this is x times the cosine of 65 is 101. In order to get x alone, what I would do is divide both sides by the cosine of 65. So x is 101 divided by the cosine of 65. And if I ask my calculator, which I know is in degree mode, 101 divided by the cosine of 65, I get a fairly large length. This hypotenuse x should be about 238 point, actually it says 986. So if I was going to round that to the nearest tenth, it would be 239.0. If I rounded it to the nearest hundredth, it would be 239.99. But anyways, it's approximately this. And then for our last question, you can see here I have from this particular angle, this is the opposite leg. So OPP, and this is the adjacent leg. So I am writing the tangent in this case because it's opposite and adjacent. So I would write that the tangent of this 44-degree angle equals x over 45. And to solve for x here, I'm going to multiply both sides by 45. So 45 times the tangent of a 44-degree angle should be x. And I'll grab my calculator. 45 times the tangent of 44, and I get 43.5 if I'm rounding to the nearest tenth. So this side right here is a little shorter than the other leg. This is about 43.5. Interesting, if this was just 1 degree more, right, it would make this an isosceles triangle, and the other one would have to be 45 also. But because it's a slightly smaller angle, smaller than 45, it makes this side slightly smaller than this side. Okay, so now we're looking at the Pythagorean Theorem. And some of these are probably triples that you can use. In fact, I believe this first one I can divide these by 100, so I would get a 1 and a 26. Oh no, if I divide it by 10, I'd have a 1 and a 26. And if I divide it by 2, I'd have a 5 and a 13. So this is a 5, 13 blank, and I forget what it is. So I'm going to go ahead and use the Pythagorean Theorem, which is kind of overkill for this, but I don't recognize this triple, I'm sorry to say. So I'm looking at 100 squared plus x squared. So again, you're looking at a leg squared times the other leg squared, and that always equals the hypotenuse squared. So I'm just on my calculator taking 260, I am squaring that, and then from that I am going to go ahead and just subtract 100 squared. So minus 100 squared. And when I do that, I get that x squared is 57,600. And if I take the square root of that, the square root of 57,600, I get the number 240. So x is 240, and if I divide that by 10 and then divide by 2, it's a 12. So I guess it's a 5, 12, 13 is the triple there that makes that easier. But I'm just using the Pythagorean Theorem. On the next one, I've got an x squared plus 35 squared equals 21 squared. So I'm looking at, and this is wrong, my other leg is 21 squared. So remember, it's the leg squared plus the other leg squared is the hypotenuse squared. So this 35 needs to be on the other side. So I'm taking 35, I'm squaring it, I am subtracting 21 squared from that. I get 784, and if I take the square root of 784, it gives me the number 28. So x is 28. And you can write it this way. It's the square root of 35 squared minus 21 squared, and that's essentially what I'm entering into my calculator. Let's go ahead and do C over here. So I'm looking at 48 squared plus x squared equals 102 squared. So x will equal the square root of 102 squared minus 48 squared. So 102 squared minus 48 squared, that gives me 8,100. And when I take the square root of 8,100, I'm looking at the number 90. So x is 90. And then the final question we have here, you can see that they're giving us both of our legs. One leg's 96, the other leg's 28. So I'm looking at 96 squared plus 28 squared, and that will equal x squared. And if I take the square root of both sides, this is one expression that I can enter into my calculator in one step to figure out the length of x. So I'm going to do that. The square root of 96 squared plus 28 squared, and I get exactly 100. And the last two, there's two more types of things on this page. The next one is factoring some quadratics. This first one is really kind of a simple case scenario, and I've done this enough that I don't need a generic area model and a diamond problem for this. If you find you still need that, it's okay, but when your leading coefficient is 1, you should be able to break this down without using a generic area model and a diamond problem. So I need factors of -12 that have a sum of 1. And I know that one of them must be positive and one must be negative. I want a positive one, so I'm looking at a 4 and a -3. So this is my answer. I can verify that by multiplying this out if I want, right? When I multiply x times x, I do have x squared. This is 4x minus 3x is plus 1x, and then 4 times -3 is -12, so it checks. So this is my answer. The next one, I'm going to go ahead and use a diamond problem and a generic area model. So in my generic area model, this is supposed to represent, this grid is the area of everything I see in this problem, right? And I see a big chunk of it is 5x squared, and up here I'm going to write 6. Now then there are 13 x's, and I need to distribute those along this diagonal, put them in these two boxes. And once I do that, then realize that the area of this rectangle would equal, the polygon's area. They would have the same value. One of the things we observed early on is that this diagonal has to have the same product as this diagonal. So that's where our diamond problems come from. 5x squared times 6 is 30x squared, and down below here I have 13x. So I'm looking for factors of 30x squared that add up to 13x, and it's not too difficult to get that, because it turns out that 3 times 10 is 30 and 3 plus 10 is 13. So I'm going with 3x and 10x. So it doesn't matter where I place these. I'll place the 3x here and I'll place the 10x here. The area in that rectangular grid is equal to this polynomial. Now now all I need to do is figure out what the factors are, right? I can just pull these factors out, and I'll have the factored form of this quadratic. So the bottom two have a common factor of 5x. Just pulling out the greatest common factor there. Across the top here, there's a greatest common factor of just 3. 3. As I go down, I have a greatest common factor of x. As I go down the other way, those have a greatest common factor of, well, it just has to be 2. So I can see that the factored form, right? The factored form can be read by looking at these pieces, right? One of the sides is x plus 2 units long. That's how long this side is. And the other side has units 5x plus 3. It's 5x plus 3 long. And when I multiply those two lengths, right, when I multiply them, I end up getting an area of 5x squared plus 13x plus 6. So this is my factored form, and I got it using a generic area model and a diamond problem. Let's go ahead and do the same thing with this problem. I am looking and I recognize that there's no greatest common factor here. So if there was a GCF, I'd like to get that out first. It would make my work easier. But 4 and 12 and 9 are not all divisible by the same value. Turns out 12 and 9 can both be divided by 3, and 4 and 12 are both divisible by 4, and 2 for that matter, but all three of them aren't divisible by something. So again, we deploy our generic area model representing the value of that polynomial. We put our 4x squared and our 9. And again, once we fill in these two boxes have to add up to 12x because it needs to represent this polynomial. How do we recognize that? Well, we use this diamond problem to help us figure out how to fill the other diagonal in. 4x squared times 9 is 36x squared, and down below I have a negative 12x. So I can see right away that I'm going to need negative factors. In fact, I know that they both need to be negative because the product at the top is positive, right? And the only way I can get a positive is by multiplying two positives or multiplying two negatives. The reason why I can't multiply two positive here is because the bottom has to be a negative 12x. So I know that I need two negative numbers to get that. The number 36, it is 6 times 6, and actually say no more. I was going to break it down further, but just in writing 6 and 6, I can see that it is definitely negative 6x and negative 6 times x. So that's it. Those two have a product of 36 times x squared, and they have a sum of negative 12x. So I'll write each of them in the box. So this means this must be a perfect square trinomial. Along the bottom here I have a greatest common factor of 2x this way, and I have one of 2x this way. If I go down, I can bring out negative 3 and bring out negative 3. So my two polynomials are 2x minus 3. That's one dimension, and the other dimension turns out to be the same, right? It's 2x minus 3. So I can write this, well, I can write it like this, times 2x minus 3. But since they're the same, I can write it as 2x minus 3 quantity squared. This last one is the difference of two squares, and I recognize that immediately. So I know I can write this as 10x minus 7 times 10x plus 7. And perhaps you don't recognize that. If it's the case that you don't recognize it, you could do this. You could introduce, there are 0 x's minus 49. You could do that, and a generic area model and a diamond problem would work. But for me, because I know that this is the difference, it's a subtraction of perfect squares, I know that this factors as the sum of their square roots and the difference of their square roots. So again, their square roots are 7, right? The square root of 49 is 7, and the square root of 100x squared is 10x. So that's why you see 10x minus 7 and 10x plus 7. And the final problems on this page are proportions. There's lots of ways you can tackle a proportion. Probably one of my favorite ways is to just multiply both sides by something to destroy all fractions. And that works nicely here. If I multiply both sides by 10, over on the left hand side I have 10x over 5, and on the right hand side I have 8 times 10 over 10. I think you'll recognize this is just a giant 1, so I'm left with only 8 on this side. And on the other side, 10 divided by 5 is 2. I have, I have 2x there. So if I divide by 2, I get that x is 4. And I can put 4 in, and yeah, 4/5 is equivalent to 8/10. For the other one, I could do the same strategy, but I think what I'm going to choose to do instead is this. It's a shortcut that logically is equivalent to multiplying both sides by something to bust up the fractions. But it turns out if you have a proportion, these diagonals would end up being congruent to each other, and it's not hard to prove that, right? It could be proven as easily as this. I could say, hey, A over B is equal to C over D, and I could multiply both sides of this by BD. I'm going to multiply over here by BD. When I do that, on this side I have B, D, and A. On the other side I have C, B, D over D, and this is over B. So all I'm doing is I'm just putting these, I'm multiplying both sides by BD. So you can see there's a BD here, and there's a BD here. It turns out I have a giant 1 on this side. There is a D over D, which leaves me a CB here, and there is a DA on the other side, DA. So you can see clearly at this point that this shortcut, A times D, that's what this is the same as B times C. That's what this is. So I show that because I don't want you to think this is some weird magical thing. It's just, this is why this works. So these cross products are equal. That means 4 times the quantity of x plus 5, and that's the diagonal that I've highlighted in green, has to be the same as 8 times the quantity of x minus 3. So here we have 4x plus 20 equals 8x minus 24. I'll take away 4x from both sides. I'll add 24 to both sides. And I get that x, when I divide by 4 then on both sides, I get that x should be 11. And to give you a sense of how I might approach checking something like that, let me start my on-screen calculator here and bring it over. If I'm looking at this calculator, I believe x is 11. So let's erase this so we can see the original problem. If I go ahead and go 4 divided by open parentheses 11 minus 3 close parentheses, you see I get a value of -2, and I want to compare that to 8 divided by the quantity of 11 plus 5, and you can see when I do that I get failure on my part. Oh, I see why this is a failure. I didn't enter 11 for the first one. That needs to be 4 divided by the quantity of 11 minus 3. And when I do that, you can see I get 0.5. So the reason why 11 is a solution is because when I place 11 into this equation for x here and here, it makes this equation 0.5 on one side and 0.5 on the other. In other words, it makes it true, right? The value 11 makes both the left and right hand side equal to 1/2.